So in the last lesson, I said that we were going to talk about the elimination reactions of halogenoalkanes to give alkenes. And don't panic, we still will. I know you were all worried there. But we're going to take a little diversion first, a little detour, a little segue. And the first thing we're going to do is we're going to talk about some ozone chemistry. Now, you've almost certainly heard of ozone. It's present in the upper atmosphere, and it's what prevents a lot of the UV rays from the sun reaching the planet, which would do a lot of damage to us as kind of slightly squashy humans. We don't really like UV radiation. And the ozone layer absorbs a lot of that UV radiation. Now, the problem here is that on our lovely Earth, which let's have a go at drawing here. So here's the Earth, and let's have some water. And obviously the rest of it is all land. Land here. Above that, we have various different levels of atmosphere. And in one of the upper levels of the atmosphere, we have ozone, and this gets called the ozone layer. Now, the problem is that recently the ozone layer was noticed to be shrinking, and specifically there were holes in the ozone layer above the Arctic. So you might have seen pictures of this in the news, where you have these pictures where they show a big hole in the ozone layer in the Arctic, and it's often done like this with kind of contours and colours. So it looks like this kind of thing. And that hole was caused by humans releasing chlorofluorocarbons, or CFCs, into the atmosphere. So for example, this is a chlorofluorocarbon. This has got fluorines and it's got chlorines on it, and it's a methane difluorodichlorocarbon. Now, when scientists realised this, there was a big international effort to prevent CFCs entering the atmosphere, and now they've been pretty much eliminated, and the ozone layer hole has started to shrink, which is great news. And it's a really good thing that chemists have been able to do, and chemists have now provided us with alternatives to CFCs that we can continue to use. If you're wondering where they get used, by the way, they were often used in fridges or as refrigerants, commercial refrigerants. I'm now just going to draw you a picture of a fridge in case you didn't know what one was. Here you go, here's a fridge with some bottles in it. But when these were disposed of, they would often release their CFCs in the atmosphere. And this is what would cause the hole in the ozone layer. I might need to label that because the quality of the drawing is not good. That's a fridge. So that was a problem, and you need to understand some of this for the AQA syllabus. So the first point is ozone is naturally present in the upper atmosphere. Humans haven't put ozone there, it's already there. Upper atmosphere. Upper atmosphere. And it's beneficial because it absorbs harmful UV rays. Absorbs harmful UV rays. Chlorine atoms are formed in the upper atmosphere by the breaking of carbon-chlorine bonds in CFCs. So you go like this: CFCs, UV, means that you end it with Cl dot, and Cl dot gives you Cl2. And this is what is doing the damage. So this chlorine, because that chlorine can then float about a bit, and then it can split up again with more UV light and form chlorine dot again. So you end up with this radical source in the upper atmosphere, and when you combine that with ozone, which is O3, 3 oxygens, then you have a problem, because now it breaks down the oxygen and gives you things like ClO dot and oxygen. And this is a problem because we now have a propagation. We have a radical reaction which has a propagation step which results in another radical, and it has broken ozone down to oxygen. And oxygen doesn't absorb UV rays in the same way that ozone does. So chlorine atoms act here as a catalyst. And they act as a catalyst because, as I said already, it regenerates the radical. So that radical can then go on and do more damage. So let's show the initiation, propagation and termination steps here. So let's say I start out with Cl, CH3, just chloromethane, very simple molecule, and let's expose that to UV light. That's going to give me Cl dot and methane dot. Now this Cl dot, so that's initiation. That Cl dot can then react with ozone, and that gives us ClO dot and O2. Now that ClO dot can then react with more ozone to give more oxygen and chlorine. And if you look at one of my additional content lectures on Udemy, then I'll explain the mechanism for some of this reaction in a simple way. So you can go there if you're interested in that. But for now, we'll leave it at this, and you just need to understand that the chlorine is a catalyst, because you'll see here it starts in the reaction, and if I go all the way to the end, there's still chlorine there, but in the process I've created oxygen, and this is actually 2O2. So I've actually created 3 oxygen atoms, and I've removed 2 ozone molecules. Sorry, not atoms, molecules. So this is a problem, and we've removed this problem by providing alternatives to chlorofluorocarbons for refrigerants. So this now leads us on nicely to talk about some elimination reactions. If we start with something like this, so this is chloroethane. If I add sodium hydroxide to this, you're saying, oh, I already know what the reaction is going to be here because we did this earlier. This is a nucleophilic substitution, so my arrow comes from my lone pair, goes to this center which is slightly positive, and it kicks out my chlorine. And I'm left with, not going to draw in all the hydrogens, you're left with ethanol. And you'd be right, that is one reaction product, but there's actually another one. You'd also be left with ethene. And ethene is an alkene. Don't confuse it with alkanes. There's only one letter difference. It's this E. So an alkane has an A there, and an alkene has an E there. And what an alkene means is it has this double bond here. So an alkene is another homologous series, and it has a double bond in it. But other than that, it's just a hydrocarbon, hydrogen and carbons, but with double bonds. And we sometimes call this unsaturated. Unsaturated. So why have we ended up with an ethene molecule when we were expecting to get an ethanol molecule? So there are 2 reactions happening here. So hydroxide is acting as a nucleophile, but it is also acting as a base. A base is something that can remove hydrogen atoms. So on the top reaction it acts as a nucleophile, but on the bottom reaction it acts as a base. Let's have a look at the mechanism for that now. So if I start out with with ethene, and let's try working backwards. So I want to finish with that, and I've got no double bond, but I've got my chlorine here, and I've got hydrogens everywhere else, and I've got my hydroxide, and it's got a lone pair, but it's going to act this time like a base, and that means it's going to remove a hydrogen. So if it acts like a base and it removes a hydrogen, let's have a go at that. So let's take a curly arrow from here, and let's go and hit this hydrogen here. Now where is this going to go? Well, it's going to go onto this carbon. So what does that leave us with? Well, let's go down here. It leaves us with a carbon with a negative charge on it. And now our carbon has only got 3 bonds because it's got that negative charge. And I've still got this other end, HCl. Now that negative charge, that pair of electrons there, can now go and make a bond between these two carbons, and in doing so, it will break this carbon-chlorine bond. Remember, this is a flow of electrons. So as the electrons flow from this negative charge into this double bond, that's a negative thing going this way. And this bond has electrons in it which are negative, so they're being pushed by those electrons in this direction. And remember as well that chlorine is electronegative, so it is pulling electrons towards it away from this carbon. So this is another example of a push-pull reaction, but instead of a nucleophile, you have a negative charge on the carbon acting as the pushing force. So what do we get when we're left with this? Well, you've probably worked it out. I've got a carbon here, it's got 1 bond, I've now formed my second bond, my other carbon's here, and that carbon's got 2 hydrogens, and the chlorine has disappeared. It's not disappeared, of course, it's here, chlorine minus chloride. And on the other end, I've got 2 hydrogens. So this then is what we wanted to get to when working backwards. This is, as we said before, ethene. And so it's important to know and understand that if you add sodium hydroxide to a halogen alkane, you'll get 2 products. You'll get an elimination product, which is the alkene, and you'll get a nucleophilic substitution product, which will be the alcohol. And in one case, the hydroxide is a nucleophile, and in the other, it's a base. Now, we've already dealt with the nucleophilic substitution earlier, and now here you've got the reaction as a elimination reaction. So you have everything you need now to address elimination reactions of halogen-alkanes with bases, and this base here, this hydroxide, it could come from a number of sources. So it could be potassium hydroxide or it could be sodium hydroxide, and you need to be prepared for either of those. But it doesn't matter, the hydroxide is the part that's doing the important work, and the work it's doing is as a base, so that means it's removing a hydrogen, or sometimes we say removing a proton, from the molecule to give you that negative charge that then proceeds to kick out the chlorine from the far side. And that's all you need. So that gives us a new homologous group to play with, and that is the alkenes. And so in our next series of lectures, we're going to look at the alkenes as a homologous series, and the functional group here is a double bond. And this leads itself to all kinds of interesting chemistries, and we're going to look at that next.